Welcome and thank you for joining the Health Effects Institute 2020 webinar series. The topic of today's webinar is Understanding Ultrafine Particles in Health and How We Can Make Progress. I'm Eliane Van Vliet, Staff Scientist at HEI, and I'd like to acknowledge Katie Walker, Principal Scientist at HEI, who co-organized today's session. Along with the rest of the HEI staff, we hope you and your families are safe and healthy during this challenging time. As you may know, we're holding 5 webinars in lieu of the HEI annual conference that was planned in Boston and had to be canceled due to the coronavirus pandemic. We're really grateful that the session speakers and chairs have agreed to present webinars instead. We also want to acknowledge those at HEI who've been working behind the scenes to transform the annual conference into this webinar series. So before we dive into today's webinar, just a few housekeeping announcements. We'll hold all questions until the Q&A answer period at the end, and questions should be submitted via the Zoom Q&A function only. You can add and upvote questions to the Q&A section at any time during the webinar. And if you experience any technical or logistical issues, please let us know via the chat window. There's a drop down for panelists, or you can email us at bigheal@healtheffects.org. We'd really appreciate your feedback through the post-webinar survey that will appear after the webinar on your screen and also emailed to you tomorrow. And finally, please visit our website for information on the remaining webinars in our series. All the sessions will be recorded and available on YouTube in the next few weeks. So today we want to tackle a long-standing debate about the independent effects of ultrafine particles on human health. And our goal in this session today is really to lay out the factors that need to be considered to move the science and the decisions about ultrafine particles forward. It's now my pleasure to introduce today's session chairs, Dr. David Foster, Professor Emeritus in the Department of Mechanical Engineering at the University of Wisconsin-Madison and a member of the HEI's Research Committee, and Dr. Alan Robinson, Distinguished Professor and Head of the Department of Mechanical Engineering and Professor in the Department of Engineering and Public Policy at Carnegie Mellon University. He is also a member of HEI's Research Committee. So we have an excellent lineup of speakers for you today with an extensive breadth of expertise. And I will now let Alan Robinson provide the introduction and set the stage for today's session.
Thanks, Eliane. If we could go to the next slide, please. So I was just going to give just a couple of remarks here to open up the session. And so as you all know, ultrafine particles have been a topic of focus for the Health Effects Institute and the health effects community for more than a decade. And I just wanted to call out the HEI Perspectives #3, which was focused on ultrafine particles that came out in 2013. And this is a very highly downloaded and referenced publication from HEI. And I just want to summarize what the conclusions were at that point. And clearly, ultrafine particles are different than larger particles in their deposition patterns and their clearance from lungs and their potential for translocation. In 2013, the review said that there was suggestive experimental and epidemiological evidence for short-term effects to ambient ultrafine particles, but this evidence wasn't consistent. And they concluded that there was not strong enough evidence to say that the short-term effects of ultrafine particles were dramatically different from those of PM2.5. The review also found that there weren't studies for long-term exposures to ultrafine particles and their health effects. And so there were a lot of questions at that time, and we periodically come back to this topic in the annual conference to get an update, and today is going to be another update about what the state of knowledge is around ultrafine particles. So if we could go to the next slide, please, Eliane. Thank you. So obviously the concern is that there's differential health impacts. Everybody knows about the health impacts of PM2.5, but ultrafine particles, as I already said, the concern is differential health impacts. And this was highlighted last week in an excellent webinar as part of the HEI series by Fleming Cassé. And he was looking at some data on particle size dependent particle size dependent translocation. And that's, I'm not going to go into the slide, but just to sort of highlight that this is an important topic that was brought up in that session as well. And it clearly showed that the smaller particles translocated much more readily than larger particles. So next slide, please. So the final sort of piece of introduction is just to talk a little bit about, some key questions to think about. And we've asked the speakers to address in the context of their talks. And so the first is, how have ultrafine particle sources and exposures changed over time? Are there regulatory drivers for these changes? Second one is, what's the right measure of ultrafine particles? Particle number concentration, particle mass, particle composition, smaller than 100, smaller than 200 nanometers, etc. Another question is, what would it take to develop robust population-based estimates of exposure to ultrafine particles for epidemiological studies? And then finally, what are the biggest knowledge gaps, impediments to drawing conclusions about the role of ultrafine particles in public health? So these are questions we've asked the speakers to think about, and we'll come back to these questions at the end, as well as the questions that you ask in the Q&A box. And we'll have a good time for discussion at the end. So thank you, and looking forward to a really productive session. And I want to introduce my co-chair, David Foster, who will introduce the speakers of today's session.
Thank you very much, Alan. It's my pleasure to introduce the first speaker, Lydia Moroska. She is a professor at Queensland University of Technology in Brisbane, which is where she's speaking from, where it is now a few minutes after midnight. So thank you, Lydia, for being with us. She is at the university. She's the director of the International Laboratory for Air Quality and Health, which is a World Health Organization collaborating center. She's co-director in Australia of the Australia-China Center for Air Quality Science and Management. She has a background in physics and conducts fundamental research and applied research in the science of airborne particulate matter, very widely published. And she is a member of another number of panels and international bodies, and is acting as an advisor to the World Health Organization. Lydia, please. Thank you.
Thank you very much. I'm not sure whether you can see my screen because there seems to be a problem here. Can you hear me?
I can see your screen, Lydia. Yeah, there it is. Yep, I can see it at least.
Okay, yeah, there was some break. Well, good morning or good evening. I'm not sure what to say when starting the presentation at midnight. Thank you very much, David, for introducing me, and thank you, colleagues from the organizing committee from the Health Effects Institute, for inviting me to talk about progress and questions about ultrafine particles. I will give a summary based on the work of a team, the thinking outside of the box team. The team consists of exposure people like myself, toxicology, epidemiology. We've worked together and we've generated the white paper, Ambient Ultrafine Particles, Evidence for Policymakers, which is now hosted by the European Federation of Clean Air and Environmental Protection Associations. The motivation for this work, in a way, was frustration at a conference just over 2 years ago in Cassino in Italy. We realized that we hear too many times and too often that there's not much known about ultrafine particles. And therefore we thought it's time to do something and to show that there's in fact a lot of known. We've met twice in Munich. We've interacted many times via Zoom meetings and other means of communication. So the work is progressing. And I will talk today about recommendations on exposure, one part of this work. I'll be talking about progress, recommendations 1, 2, and 3, and future recommendations 4 and 5. So recommendation 1, to quantify ambient quasi-ultrafine particles in terms of particle number concentration in a range at least down to 10 nanometers with no restriction on the upper limit. So that's important, at least down to 10 nanometers with no restriction on the upper limit. One addition here is in relation to toxicology. While the toxicologists often say that they would prefer a mass or surface area, however, the agreement of the team was that for practical reasons, particle number is preferred, particularly where particle size distribution is known. Significance of this? Well, this is an essential criterion for design of exposure and epi studies, for carrying out meta-analysis, the choice of the instrument, choice of the designs, and the decision of which studies to include in the meta-analysis. A short background. Well, we all know what's the definition of ultrafine particles, a particle size about 100 nanometers in diameter or less. And if we have a size distribution of the particles like that one shown here, we can extract from this size distribution particles below 100 nanometers. However, if we use CPCs, the question is what to do. This definition allows, or this recommendation allows that both SMPS and CPC data can be used. And this is because the tail on the larger particle size is insignificant compared to the whole distribution. Also, the error or uncertainty due to the missing first few nanometers could be calculated or corrected if the cutoff point is 10 nanometers, and in fact is negligible for the lower size range. A little background to this, based on two spectra presented, one from Barcelona, one from Casino. If the cutoff point is 10 nanometers, so we can see that for situations like this, morning traffic or during the day, it's an insignificant part which is missing. That's slightly more missing during the new particle formation event. However, if, for example, the cutoff point was at 20 nanometers, most of the nucleation would be missing, like this one, initial stages 65% and 42 for fully developed nucleation event. Well, recommendation 2, the following 24 hours mean particle number concentration can be considered typical. So for clean environments is below 10 to the third particles per cubic centimeter, and for urban backgrounds below 10 to the fourth particle per cubic centimeter. On the other hand, for hourly means, typical concentrations are considered below 10 by 2 by 10 to the 10 to the fourth. Important also to mention that uncertainty in the calibration, which is often asked in this situation, well, varies, and it's higher for smaller particle concentration. It is 30%, it is 10% for particle 10 to the fourth. Now, significance of this, at the moment, there are no reference or guideline values for exposure to ultrafine particles, and specifically the WHO 2005 guideline documents states that the existing body of epidemiological evidence is insufficient to conclude on exposure-response relationship to ultrafine particles. Well, of course, this is what we are providing is not exposure-response relationship, but these typical values can serve as a comparative reference. And importantly, the WHO is currently updating its air quality guidelines and may consider this information. A background, a review which we've conducted in 2008 for different environments for which the data were available at the time showed exactly already this, that for clean environments, it's below 10 to the third, urban background around 10 to the fourth, and near roads, tunnel, another order of magnitude higher. So this was then what's the situation now. based on this review of concentrations in 10 studies around the world, we basically can see the same situation, that for urban background, the concentrations are about 10 to the 4th. Recommendations 3, the following should not be used as proxies of ultrafine particles, which is PM2.5, CO, NOx, or black carbon. Significance of this: using other pollutants as proxies of exposure to ultrafine particles leads to exposure misclassification. We've seen very clearly that there's little or no relationship between particle number, concentration, and PM2.5, and we understand why. There is a somewhat better relationship between particle number, concentration, and traffic emitted gases or black carbon, but it's specific to the specific environments, and therefore universal usage of such relationship would lead to misclassifications. Background to this, this is based on the paper which I just mentioned. This is relationship between particle number, concentration, and PM2.5. Well, for these two cities, well, as you can see, despite these circles here and a Thames curve, there is basically no relationship. And again, as I say, we can understand this. Another point to mention is this situation. In this study, we've looked, or a team looked at the long-term trends in particle number, concentration in the cities for which the data were available. I'll just present 4 of them here. And as you can see, for these cities, there was a decrease in particle number, concentration over time. We've also looked at PM2.5, and the decrease was to much lesser extent. But importantly, the years in which the reduction in the concentration occurred do not coincide for PM2.5 and PNC, which means that there are different drivers for this. Recommendation 4, regulatory air monitoring strategy should be extended by integration of ultrafine particles for reporting purposes. Now, and the specific importance of this is to be able to conclude on the relationship and the impact of primary versus secondary particles, therefore the parameters which need to be monitored as such to provide information for this. Now, as a background, I'd like to mention the study conducted by Spanish colleagues in 3 cities in Spain, Barcelona, Huelva, and Santa Cruz de Tenerife. What the colleagues did, they divided total particle number, concentration into 2 components: primary plus nucleating immediately after emission and correlated with black carbon, and secondary N2 with low correlation with black carbon. So what they found is that mean ultrafine particle concentration were similar in the 3 cities. Black carbon was high in Barcelona and Tenerife, but very importantly, associations with daily mortality were different. In Barcelona and Tenerife were with N1, which is primary particles, in Huelva with N2 with secondary particles. Well, none of these associations were statistically significant. Nevertheless, these differences point out to the need of a better understanding of the impact of primary versus secondary particles. Now, and the last recommendation is about the need for efforts to utilize the emerging science and technology to advance approaches to the assessment of exposure to ultrafine particles. Well, over the last years, many things have progressed. We've got much better modeling tools. We can use more monitors. You can utilize mobile platforms. They're just amazing tools which can be used now, which could give us more information and better information about ultrafine particles for the purpose of epidemiological studies and management. So we are not out of the box yet, but on the way. The group continues working. We've already had another paper submitted based on this work, and we keep extending this work. Thank you very much.
Thank you, Lydia. That was a very nice overview of an extensive body of work. Thank you very much. The next speaker, Tim Dahlman, is a member of the research staff at International Council for Clean Transportation. He's a senior researcher there, and he's working on clean air and passenger vehicle teams where he's applying his expertise in motor vehicle emissions, currently focusing on assessment of air quality impacts of on and off-road vehicles and equipment. Tim is a BS in Civil and Environmental Engineering from the University of Wisconsin-Madison. He has MS and PhD in the same field from University of California, Berkeley, and has done postdoctoral research as a fellow in the Center for Automotive Particulate Studies at Carnegie Mellon University. Tim, thank you very much.
Thank you, David, and thank you to all of the organizers for this seminar. I think it is a really nice set of speakers, and I'm happy to be involved as part of this discussion. So jumping right into things, I wanted to go over a few of the key themes that I'll be talking about during my presentation. The primary goal is to talk about the impacts of the US and European Union regulatory programs on vehicle emission control technology developments and how those developments have affected ultrafine particle emissions. I want to pull in some real world emissions data to look at how these regulatory programs have affected actual emissions in real world settings, and then extend the discussion past just the US and EU to look at some of the global developments in vehicle emission control programs in other regions of the world and how that might affect ultrafine particle emissions moving forward. And finally, the last two topics will be the implications for other mobile sources, such as non-road engines and two-wheelers of the control of light-duty and heavy-duty vehicle emissions. And finally, future developments in the United States and EU regulatory programs that are ongoing right now. So I wanted to start with perhaps what is one of the most important developments in the control of particle emissions from motor vehicles over the last decade, which has been the adoption of standards for heavy-duty diesel engines in Europe and the United States that effectively force the use of the best available control technologies to control emissions from these engines, which is the diesel particulate filter. In the US, 10 milligram per brake horsepower hour PM mass limit was introduced in 2007. That effectively required the use of a DPF to meet that limit. The Europe limit, prior to the current standards, which are Euro 6, Europe controlled particle emissions using a PM mass limit. The Euro 6 standard, they also introduced a solid particle number limit. And the effect of that introduction has effectively, as in the US, effectively mandated the use of DPFs in heavy-duty diesel engine designs. At the bottom of the slide, you can see kind of an example of the after-treatment control technology package for modern heavy-duty diesel engines sold in the US and Europe, with PM control through the DPF and NOx control through SCR systems. The impact of the deployment of DPFs in Euro 6 vehicles is readily apparent in real-world emissions data. So these two plots show results from an in-use measurement study conducted in Sweden that measured emissions from about 550 in-use heavy-duty diesel trucks of various ages and emission control technology packages. Here on the left, we can see for emissions of PM, as we go from Euro 3 to Euro 6, we can see at the implementation of the Euro 6 standard, an order of magnitude decrease in the median PM emissions from the trucks in the sample. And those emissions are well below the regulatory standard. For particle number emissions shown in the right panel, we see a similarly large reduction in the median emissions with introduction of the filter forcing Euro 6 standards. I will note for the PN emissions, we can see a wider spread in the distribution. That speaks to the relatively important impact of a small fraction of high emitting vehicles in the sample. Turning now to the US, this plot shows similar results from a study at 2 different locations in Oakland, California. It shows, again, in this case, black carbon emissions from diesel trucks by engine model year, separated by the 2 locations, with the red bars showing pre-2010 model year trucks that were equipped with DPFs but were subject to different NOx standards. So again, here in this project, the researchers found a similarly large reduction in average black carbon emissions with introduction of filter forcing standards. However, they also noted the widespread in emissions from these DPF-equipped trucks, in particular the pre-2010 trucks. And they attributed that in part to the deterioration of the DPF system over time, which was especially apparent in kind of the first generation of the DPFs on those earlier trucks. And it's also an important point to note that given the spread, the use of monitoring and in-use monitoring to detect any sort of DPF deterioration will become important. These systems are very effective when they're working well, but if they're not, it's important to be able to monitor and identify those cases where you're not getting the full level of control over the entire useful life of the vehicle. So turning now from heavy-duty vehicles to light-duty vehicles, I wanted to go through the current standards and a few things that are different in the approaches of the US and Europe when it comes to regulating particle emissions from light-duty vehicles. In the US, the current standards are the Tier 3 standards. These standards are fuel and technology neutral, that they apply to equally to both gasoline and diesel vehicles. The Tier 3 standards set a PM mass emission limit of 3 milligrams per mile. California has implemented separate Lev 3 standards, which will phase in a more stringent 1 milligram per mile limit beginning in 2025. In the EU, the current stage of the Euro standard is stage 6. And again, similar to the approach with heavy-duty vehicles, the European standards for light-duty vehicles also incorporate a particle number emission limit in addition to a PM mass limit. However, I will note that those PM and PN limits only apply to vehicles equipped with diesel or gasoline direct injection engines. Gasoline engines with port fuel injection engines are not subject to the PN or PM limits. In addition to these limits, the EU program also differs from the US in its use of real driving emission test for vehicle certification. As I'll be talking about in a few slides, these differences in the regulatory approaches to particle emission control have influenced emission control technology adoption for light-duty vehicles. Similar with heavy-duty vehicles, I wanted to pull in some real-world data to show the effects of the increasingly stringent regulatory programs on PM emissions. Here I'm showing the results from a remote sensing study the ICT conducted in London in 2017. Results are shown for PM emissions from passenger cars disaggregated by engine type, diesel or gasoline, and Euro emission standard. So 2 things to point out here, that gasoline PM emissions are historically low near the detection level of the instrument. With the diesel emissions, we can see the median and average emissions coming down over time with gasoline-like emissions measured at the Euro 5 level and Euro 6 level when you have DPFs gaining wider market share to control emissions from these diesel light-duty vehicles. Another key driver of kind of the development of light-duty vehicle engine technologies and emission control strategies has been the implementation of fuel economy and CO2 emission standards in the US and Europe. And one thing that has done has been served to really drive the market penetration of gasoline direct injection engines, which have been used increasingly to lower CO2 emissions, increase efficiency. So here in the plot, we can showing some EPA data looking at the market penetration of GDI engines over time. So starting in about 2008, there's been pretty rapid growth. And as of 2019, GDI vehicles accounted for about 50% of the light duty vehicle production share in the US. And it's important to note, it has implications for ultrafine particle emissions in the sense that gasoline direct injection engines typically are associated with higher levels of PM and PN emissions relative to a comparable port fuel injection engine. In the United States, the Tier 3 PM limit, which I mentioned earlier, can be met without the application of the best available control technology for controlling PN emissions from GDI engines, and that's the gasoline particulate filter. In contrast, the new real driving emissions, so the on-road particle number limit that's being introduced in Europe, is expected to drive the wide deployment of gasoline particulate filters in the EU. New GDI vehicles sold in the EU are now expected to have GPFs installed on them. So I'm kind of summarizing what I've been talking about with heavy duty vehicles and light duty vehicles. One key takeaway here is that the widespread use of DPFs for diesel vehicles and the increased GDI market share is expected to really change the nature of urban vehicular particle number emissions. And that's something that we'll hear a bit more about in the next talk from Maddie. So now turning from the US and Europe, I wanted to briefly go over some of the developments internationally when it comes to the development of emission control program. Here I want to focus on heavy duty vehicles and engines and the expansion of Euro 6 equivalent standards into major vehicle markets. So this chart shows the development of emission control programs in a selection of G20 countries. I want to point out the blue is an indication of when Euro 6 equivalent standards have been or will be implemented in each country that has achieved them. I want to point out between 2020 and 2023, Euro 6 equivalent standards will be coming online in China, India, and are expected in Mexico and Brazil. Additionally, not shown on this chart, Euro 6 standards are also be coming online in Colombia as well. So these 5 countries are expected to, in 2025, account for 1/3 of global sales of new heavy-duty vehicles. So the fact that they'll have, are expected to have these filter forcing standards online at that time will really drive reductions in PN emissions from this important source category in each of these countries. The ICT has done some analysis and projections of how the use of DPFs to control emissions from heavy and light duty diesel vehicles will change over time. These charts just show our expectations for the percentage of new vehicle sales that we expect to be equipped with DPFs in 2020 and 2025 for heavy duty trucks and buses on the left and passenger cars on the right. So in 2025, we expect that about 70% of new vehicles sold globally, or new diesel vehicles sold globally will have DPFs, whereas for passenger cars, that number will be about 90%. So that's very important progress, and that will help to drive down PN and PN emissions in these regions. However, more will be needed to be done in order to really drive down global emissions. So here, again, we have some projections that we published last year on how black carbon emissions are expected to change, or black carbon emissions from diesel vehicles are expected to change under different scenario projections. So just looking at the counterfactual standards in force in 2015, we can see that standards adopted as of 2019 are expected to really drive down BC emissions, with the Euro 6 equivalent standards in China and India being very important in that development. However, with the growth of the global vehicle fleet, we can see that more is needed to be done. More countries need to get to Euro 6 in order to really drive down emissions. So turning now and thinking about, at least in the US and Europe, where we have these filter forcing standards for diesel vehicles, as emissions come down from kind of historically important sources, what other sources might become relatively more important. So here I'm showing an example of for non-road engines and equipment. Historically, the EU and US standards have been harmonized. Recently, the EU has implemented stage 5 of their emission control program for non-road engines, which includes a tightened PM limit as well as a particle number limit. So that will effectively force the use of DPFs on new non-road engines sold in the EU. In contrast, the US Tier 4F standards just rely on a PM mass limit to regulate particle emissions. And an assessment we did a few years back shows that the Tier 4F limit can be met without the application of a DPF. So the US non-road engine standards are not forcing the use of DPFs. So especially for equipment that's used in urban areas, this is very important that the best available control technology is not currently being applied in all of the engines that are being sold in the US. Similarly, for cities, especially urban areas where there's high percentages of 2- and 3-wheelers in the fleet, the control of light-duty vehicles and heavy-duty vehicles can increase the relative importance of these sources. So this plot shows CO2-specific PM emissions for different vehicle categories measured in Paris in 2018, a remote sensing study that we led there. Just quickly to point out, we found that when expressed on a CO2-specific basis, PM emissions from L category vehicles, which are mostly motorcycles and mopeds, on average look a lot like the level of emissions from diesel cars. And if we just look at the current standards, we found that the CO2-specific PM emissions for the Euro 4, the current standard L category vehicles, were higher than those of Euro 6 diesel and petrol cars. So in European cities or other cities internationally where you have a large percentage of these vehicles in the fleet, they could become an increasingly important source of PM and PN emissions. Finally, I think we're running short on time here. Just to speak quickly about future developments in the US and EU. The European Union is currently working on developing post-Euro 6 standards with the key objective of ensuring vehicles are as clean as possible under all driving conditions and over their entire useful life. With respect to ultrafine particles, key aspects that are under discussion include the extension of the particle number limits to other vehicle types through fuel and technology neutral standards, and the change to the measurement program for particle number count to include particulates between 10 and 23 nanometers. And finally, there's some discussion of also addressing non-tailpipe emissions. In the US, most of the focus now is on heavy-duty NOx emissions. California is pursuing a heavy-duty low NOx program, and the EPA Cleaner Trucks Initiative was recently announced to also look at heavy-duty NOx emissions. So in the interest of time, I'll just my key point I want to make here is the first point that Euro 6 and EPA 2010 standards have made DPFs universal on new trucks and buses sold in the US and EU. And the expansion of US Euro 6 equivalent standards to major markets is a major development in heavy-duty truck and bus emissions control. However, further expansion is needed to curb global emissions from the sector. With that, I'll thank you.
Thank you very much, Tim. That was an interesting and significant perspective of what's happening internationally, both in terms of countries in their phase-in of different emission standards and sort of what the issues are in terms of what's happening globally as well. So thank you very much. Our next speaker, Matty Marique, is from Ford Motor Company. He is the technical leader in the research and advanced engineering activity at Ford, where he leads the Vehicle Emissions Research Laboratory. And within the vehicle and mobility industry, he is well known for his expertise and research on combustion aerosols and vehicle emission measurements. Maddie, thank you.
Well, thank you very much, David, for a nice introduction. And thank you, Tim, for previous talk sort of setting the stage on emissions regulations and emissions around the world. What I want to talk about today is ultrafine particles in a changing landscape of engines and emissions controls. What I want to accomplish with this is to give you a bit of history of where we've come from. So basically what PM emissions were like before particle after treatment. Then talk a little bit about where we are now. So the state of having gasoline direct injection engines, for example, and then concerns in Europe about particle emissions in cities and so forth. And then talk about where we are headed in the future. So more electrification and concerns about non-tailpipe vehicle-related emissions. So where have we come from? A good demarcation time is the 2007 and 2011 timeframe. In 2007, the EPA introduced its 10 milligram per horsepower hour PM emissions limits for heavy duty vehicles, as Tim mentioned. Basically, this was sufficiently stringent that it required the use of diesel particulate filters to remove particles before they were emitted. In the European case, the legislation proceeded a bit differently. In that case, they turned to a particle number standard in lieu of a mass standard, but that particle number standard was sufficiently low to also force PM filters. What about gasoline vehicles? The graphic here at the top right displays particle mass emissions per kilogram of fuel for various types of vehicle technologies. So in this white panel, we have gasoline vehicles from pre-low emission California LEV standards to LEV 1 and LEV 2, and compare that with the diesel emissions before diesel particulate filters. So on this scale, these diesel emissions are about 25 times higher than gasoline vehicles of that vintage. The reason for this is because gasoline vehicles have to meet low gaseous, that is NOx and hydrocarbon emissions. And to do that, to get NOx and hydrocarbons down at the same time, three-way catalyst relies on stoichiometric combustion. So very tight air-fuel control. And when you burn something at an equivalence ratio of 1 instead of around 1.85 or so above that, you make essentially no soot. The soot limit that you need equivalence ratios of about 1.8 or higher. So it's basically a pleasant byproduct of catalyst technology was low gasoline PM emissions. In the diesel case, where do we get particulate matter from? In the diesel case, a fuel jet is injected into the engine cylinder. The piston is raised to compress that. And when the compression gets high enough, the compression heating causes combustion. So you can see the combustion here from the yellow-orange color. That's soot being produced, and then at a high enough temperature that it incandescents to give that color off. As this burning cloud of rich in fuel disperses into the cylinder, it oxidizes with the excess oxygen that's present during diesel combustion. So about 95% actually burns up before it's emitted. But the rest that's emitted has a characteristic type size distribution. This graph here displays particle size across the page and during a drive cycle with time running into the page, and then particle concentrations plotted vertically. So characteristically, the particle size here falls into two different categories. This sort of what we call soot or accumulation mode. These are mostly soot particles. That would be those particles created in the engine, solid. And then there's a second mode of 10 to 30 nanometer particles, but these are largely, not all, but largely liquid particles that form when the exhaust cools and particles condense as they exit the tailpipe into the atmosphere. The regulated PM 2.5 category extends well above the size of these particles. The ultrafines that we're talking about are a bit ambiguously defined in the literature. Often about 100 nanometers is taken as a demarcation point, but you can kind of see from this size distribution here that the 100 nanometers falls well sort of in the middle of that soot range. And so in terms of combustion engines, this differentiating between particles less than 100 and greater than 100 doesn't make particularly a lot of sense. Let's take another look at some of these emissions before the diesel particulate filter. This photo here shows a filter that was collected during an FTP test from a non-DPF diesel vehicle. It's black from the soot that's accumulated. If you look at this soot under a microscope, it's got its characteristic fractal aggregate morphology formed from primary particles like here that range from about 10 to 30 nanometers typically. People have taken a lot of studies of what the composition is. Typically, these sort of diesels had roughly 75% soot, which could have been coated with organic material, and then about 25% semi-volatile, which consisted of maybe thousands of specific hydrocarbon compounds, such as from lube oil. And in the past, when fuel contained a bunch of sulfur, like 300 parts per million, then some sulfate, current fuels are about 10 ppm sulfur or less. All right, so where are we now? The big changes that have occurred recently, say since about 2011, 2013, 14, are the large introduction, as Tim mentioned, of these gasoline direct injection vehicles into the market. These are primarily being produced to lower CO2 emissions relative to conventional gasoline vehicles. California and the US then proceeded to make new regulations. These were basically to reduce from the existing 10 milligrams a mile down to 3 milligrams a mile as a way of preventing backsliding. The gasoline vehicles of the time were well below the 10 milligram per mile limit, and they didn't want new vehicles coming that were going to be closer to that 10 milligram per mile limit. The EU similarly extended the solid particle number to cover these GDI engines. It's interesting to kind of take a look at the difference between, or the relationship between particle number emissions and mass emissions, as in this graphic in the lower left. So we have mass on the horizontal axis, number on the vertical axis. The mass emission standards in the US and the future one of 1 milligram per mile in California on the horizontal axis here, and here's the 6 times 10 to the 11th particles per kilometer EU standard. And this kind of shows the trend of the emissions. These vehicles up at the top right are high mass, high number, or non-DPF diesel. Here are some early GDI vehicles. As the technology's gotten better, these have dropped down into this range. And this scatter here is basically a result of measurement uncertainty largely. If we take a look at a filter that's collected nowadays under these lower emission standards, it's not black anymore, it's typically gray. You collect only about 40 micrograms of material over a regulatory test. Out of that, 5 or 10 micrograms might be a gaseous artifact. These filters will trap gases in addition to particles. The filters themselves weigh 150 milligrams, so you're really measuring quite a minute amount of material, you know, before you weigh the filter before and then after, so it's very hard to measure this by a filter. Interestingly, the composition has remained somewhat similar. It's a roughly still 75 to soot and 25% semi-volatile. So what's different about a GDI engine? The GDI engine has a fuel injector that injects fuel spray directly into the cylinder. remember I said that gasoline vehicles, you want to burn, you want a nice, well-mixed air-fuel mixture at stoichiometry. So they're counting essentially on this fuel spray to evaporate and mix nicely before the spark is set off to ignite the fuel-air mixture. Most of the time that works, but you can imagine something like during a cold start, not all of the fuel evaporates and may hit the piston or the walls. So here in the top right is a optical engine photograph of fuel being injected. You can kind of see the piston surface down here. Once the spark is ignited, you can see this, right? So here's the top of the piston. Under these conditions for this photo, some of the fuel hit here, and you have the so-called pool fire. The yellow again showing the incandescing soot that's formed. So what's the characteristics of this soot? It's mostly very similar to diesel soot. Yes, there are published literature photos of particles that are a little bit strange looking, but most of them are still these kind of fractal agglomerates, and they're 10 to 30 nanometer primary particles linked together in this fractal-like morphology. If you took a look at the size distribution is again fairly similar to what we saw previously with the diesel. Here you have a drive cycle over time and distance going or particle size going across the horizontal axis. You have again 70, 80, 90, 100 nanometer soot particles, accumulation mode particles that are formed in the engine cylinder, and then some nucleation mode particles that are again in the 10 to 30 or so size range. The biggest difference between GDI engine and diesel emissions is really the temporal dependence, where the GDI engine emissions are often very much dominated by cold start emissions. After the engine's warmed up, the fuel mixes quite well under most applications, and you can get down to very clean sort of normal type or gasoline emissions levels. The composition of these particles tends to change with driving condition. This graph shows the total PM mass measured gravimetrically on the horizontal axis versus the soot mass measured photoacoustically on the vertical axis. Under FTP driving conditions tests, this is from a variety of vehicle tests, some lower emitters, some higher emitters, but you can see there's quite a nice trend. We're about 70, in this case 79, fairly close to the 75 I said before. % of the particulate matter is soot. But when you go to a US06 or aggressive drive cycle, that fraction can often drop to considerably lower, here roughly around 30%. Aggressive drive cycles also affect the size distribution. So here again is a US06 example. From 0 to 600 seconds, to 0 being the start of the US06 cycle. You can see initially the emissions are quite low. There's almost nothing emitted, but about 150 seconds into the drive cycle, you see a steep increase in the number of 10 to 30, 40, 50 nanometer particles that are emitted. This coincides with the high speed portion of that drive cycle, where exhaust temperatures can get quite hot, 600, 700, 800 degrees Celsius. And so some of these emissions are mostly semi-volatile. Some of them may come directly from the engine, but others can also come from heating the exhaust pipe, heating the catalyst, heating the muffler, even heating the sampling system and desorbing stuff that may have deposited there before, and then that forms semi-volatile droplets when it cools. Where are we headed in the future? The real world emissions are becoming more and more looked at, not just laboratory testing. Gasoline particulate filters are being explored and actually being put on already with vehicles that are currently sold, GDI vehicles. There's increased interest in electrification, including hybrids and plug-in hybrids, and increased attention on battery, brake and tire wear PM. Hybrid vehicles are an interesting opportunity to lower PM emissions because they decouple the driver demand for power to the wheels from the engine. So one can now think of spending a bit more time optimizing the engine for better emissions, and then utilizing the electric motor and the battery to produce power when the driver needs it. Vehicles are also becoming smarter, so there's opportunities to tie the vehicle into traffic information, vehicle connectivity, and so forth. For example, to find a better path home on the commute that would emit less particulate into the atmosphere. Gasoline particulate filters can significantly reduce the PM. They're just about as effective as diesel particulate filters. So here on the left, we have an example measured upstream of a vehicle equipped with a GPF. So you can see here's the soot mode, and there's some nucleation particles. When you look downstream of the GPF, then that's very much lower emissions. Interestingly, I should have mentioned that the GPF will remove these. It removes the solid particles. These particles are really mostly in the gas phase as they pass through the GPF, and they're eliminated more by the catalyst or the catalytic component of the GPF than the filtration portion of it. The big challenge with GPFs is to reduce the back pressure that putting a filter in an exhaust stream incurs. The back pressure will then reduces fuel economy. So the idea of GDI vehicles was to improve fuel economy. You don't want to put a GPF in there, improve the particle emissions, but then reduce that fuel economy benefit that motivated GDI vehicles in the first place. Non-tailpipe PM is becoming more interesting. I only have this one slide to give you a little bit of idea of what it's like. So on the top right here, we have a rotor and a caliper. So this caliper has brake pads that are going to be pressed when you want to brake on either side of the rotor. That incurs friction. Friction slows your vehicle, but that friction also leads to abrasion. That abrasion can make micron-sized particles, as illustrated in this photograph in the lower left, and a lot of this falls into the PM10 and PM2.5 category. So this is the grinding type of particle debris that you get, but the heat will also cause combustion-like events. The brake pads are composite materials that include organic binders in them. You get those organic binders very hot, they can essentially burn or smoke, as shown in this photograph, a sort of extreme case of smoking brakes. These might occur during very high aggressive stopping or long, prolonged sort of going down a mountainside type stopping. All right, with that, let me summarize. There's been a lot of progress in terms of technology to lower mass and number, and these have decreased substantially to keep pace with the regulations. The particle types themselves largely remain the same. There's still accumulation mode particles, there are soot mode particles, there are nucleation particles that are mostly semi-volatile. Just the numbers of them have come down quite a bit. The relative composition has changed somewhat. The soot and sulfate are perhaps down a bit and organic materials up a bit. So how does this all relate back to this ultrafine question that we're discussing? Well, the use, as I mentioned, in the literature is often ambiguous. The choice of 100 nanometers that people have often used does not really make sense for combustion and vehicle tailpipe emissions. If one had to pick, maybe something like a half a micron might make a little bit more sense. I would argue that size is important in the question of how particles penetrate into the lung, but after that, I think other things become more important, such as the properties of the particles. We heard in the first talk, measurement of 10 nanometer particles and so forth in the atmosphere with CPCs, but a lot of those are liquid particles, and they're going to behave a lot differently in the lung than solid particles that could translocate. I was happy to see that in the previous HEI particle components and associated health effects webinar, that this is a question that is becoming, being brought more into the mainstream, and it's not just a question of the particle size. With that, thank you very much for your attention.
Thank you very much, Matty. That was a very nice overview and introduction to what goes on in the engine, sort of at the source, if you will. The next presenter is Albert Presto. He's an associate research professor in the Department of Mechanical Engineering at Carnegie Mellon University, where he's also a member of the Center for Atmospheric Particles. His research focuses on urban pollutant emissions and subsequent atmospheric transformations. He has a BS and PhD in chemical engineering. Albert.
Sorry about that. I was muted and couldn't unmute myself. All right, thank you for that introduction. So I'm going to talk some about sort of longer term trends in interurban ultrafine particle levels. I really should say North America rather than the United States, and trying to link that to exposure. So I want to group this into sort of three sets of questions about UFP exposures. So the first set of questions has to do with concentrations and spatial temporal trends. Basically, what are typical concentrations now? How have they changed, over time? And what are sort of the inter and intra-city spatial patterns? And then after that, I want to talk about sources. Particularly, we're going to talk about traffic and nucleation as sources, and how do those interface with the trends that I'm talking about in the first section. And then lastly, I want to link this to exposure and talk about sort of what is the current ability to estimate UFP exposures and what would be needed to improve exposure estimates. So I want to start with a reminder, and that reminder is there is no regulatory standard for UFP measurement or quantification in the US. And this is something that came up some in Lydia's talk. And so I'm going to use particle number count, or just PNC, as our UFP surrogate. And so any data I present will be from a particle number count perspective. Second reminder is that, at least in North America, UFPs are a really data poor pollutant. And here's a way to illustrate that. So here is the EPA monitoring network for PM 2.5. Lots of sites spread across the country, multiple sites in cities. And these are by and large collecting data in real time. There's a history that goes back, at this point, basically 2 decades. So there's lots of data to work with. Here is the current EPA UFP network. It does not exist, right? UFPs are not a criteria pollutant in the US, so there's not a nationwide network. There's, of course, data collected, but it's not sort of in any sort of systematic fashion like we have for criteria pollutants. And so I'm going to talk about data from a handful of locations where there's sort of longer term measurements. And so just to highlight them, California has in recent years started monitoring ultrafine particles. So I'm going to talk about a few locations in the Bay Area and about 4 in the Los Angeles area. And then in the eastern part of the continent, sort of longer term data in Boston, Rochester, Toronto, a couple years of data in Pittsburgh. And then right in the center, I'm going to use there's a site in rural Oklahoma that's run by the US Department of Energy that I'm basically going to use as a reference site. We'll sort of use that as the continental background and compare things based on that Oklahoma site. So to start, let's just look at the long-term trends. And I'm going to show several figures that look like this. This is a time series. We're on the left axis is the absolute particle number concentration, and the right axis, it's normalized to 2006. And in any of these times I'm doing normalization, I am treating 2006 as my base year. And if I want to do this sort of 10-year comparison from 2006 to 2016, I really only have 4 sites with data over that whole time. That's Boston, Rochester, Toronto, and Oklahoma. But what we see over that time is concentrations fell by about 30%. Over the same time, nationwide, PM 2.5 fell by about 35%. And this is an example of co-benefit, right? There's been reductions in direct PM2.5 emissions, and then also emissions of secondary PM2.5 precursors, and that's led to a reduction in particle number concentrations. There's a lot of variability in particle number concentrations. So if we look across these cities that I showed on the map a few slides ago, right now we're showing, the annual average in about 2017, and it's ratioed to this site in Oklahoma, and we see a lot of variability, right? Rochester is pretty similar to that Oklahoma site, and you go all the way to the left, in Oakland, it's a factor of 7 higher. If we look at the absolute concentrations of those cities, we get a range from less than 5,000 particles per cubic centimeter in Oklahoma. A lot of the cities in the middle, sort of LA, Toronto, Boston, Anaheim, Pittsburgh, those are sort of urban locations. They're about 12 or 15,000 particles per cubic centimeter. And in Oakland, it's above 25,000. Now, the sampling locations are different in all of these cases. So it helps to know that the Oakland site is near a highway, and a lot of these other sites are sort of on some spectrum between urban and suburban. And so one question is, how much of what looks like intercity variation on this slide is really just specific to the sampling site? And so one way we looked at that was we put together a rotating network of 30 locations around Pittsburgh. And what we found is that sort of long-term average particle number concentrations varied by like a factor of 2 to 3 at urban scale. So, the sites on the right that are sort of near highway or near industry are a factor of 2 to 3 higher than sort of urban background locations. And Pittsburgh is not necessarily unique. One way we looked at that was by doing mobile sampling in a few different cities. So on the left here is an image of our mobile laboratory, and then just some of the driving traces. The idea with mobile sampling is you can cover a big spatial area, and you can get a sense of what the spatial patterns are, in a bunch of different sort of land use classes. And so we did this mobile sampling in 3 different cities. So in Oakland, Baltimore, and Pittsburgh, and the box plots represent the variability in each of those cities. And so there are 2 sort of take homes here. The first is that if we look at the intra-city variations, right? If we take the whiskers, the whiskers show the 10th to 90th percentile, that variability is about a factor of 2 to 3 in all 3 of these cities. And then if we sort of compare the means across cities, which are in this case the red dots, there's inter-city variability is about a factor of 2. Right, so it does matter where you are in a particular city, so we sort of get factors of 2 within cities and between cities. The other thing to, of course, take home is that particle number variations are bigger than particle mass variations. So if we go back again to these locations in Pittsburgh, and then look at the PM2.5 in those areas, the variability in PM2.5 is smaller. It's less than a factor of 2, but there is some spatial correlation, right? The places that are generally higher in particle number are also generally higher in PM2.5 mass, and that's source driven. If we do sort of the same comparison across all of these cities, across all of these locations I showed before, again, here's our variability in particle number across all of these places across North America. We can put up the same sort of plot for PM2.5, which I'm showing now in the red, and the variability is smaller. Right, so if we look at the ratio to rural Oklahoma for PM2.5 in all of these locations, it's plus or minus 50% at most, whereas for particle number, we're getting sort of, ratios up to 7. Right, so PM2.5 mass is less variable than particle number. So just to summarize on these trends, typical urban concentrations are about 10,000 particles per cubic centimeter. Decreased about 30% over a decade, and there's sort of factor of 2 variability within and between cities. So next I want to talk about 2 important sources. These are traffic and nucleation. So there's lots of data to show that traffic emissions have gone down, and so this is one example of that. And so this is a synthesis of a bunch of studies of near road particle number concentrations, right, measured sort of next to a highway over time. And so there's been a big decrease. So, in sort of year 2000 or 2001, near road concentrations were, above 100,000 up to 200,000 particles per cubic centimeter. And now they're basically an order of magnitude lower. That vertical dashed line is 2007. That's the institution of the DPF rule that was just talked about in the last 2 slides. And we see a lot of the reduction occurred before that rule went into effect. And so there's other information, there's other data showing that the traffic emissions have gone down, but this seems to be a consistent story that the traffic emissions of PNC have gone down. The other driver I want to talk about is nucleation. And so this is a common way to show nucleation. This is what's called a banana plot. So basically at point D, we get new particle formation, right? So nucleation is formation of particles from vapors via chemistry. And so these particles show up at point D, and then they grow up to point E, and this is what's called this banana type growth. And this is often in the eastern US, at least, driven by SO2 conversion to sulfate. And so we did some work. We showed that nucleation fell by about 50% in Pittsburgh between 2002 and 2017. There's similar data from other cities. And a lot of that's tied to reductions in SO2 emissions. So either we've phased out coal-fired power plants or put scrubbers on those power plants. SO2 emissions have gone down by 80 or 90% in the last few decades, and nucleation has fallen in turn. And so just to summarize on the sources, traffic, especially the urban scale traffic, is a really important source. It drives a lot of the spatial variability within cities. And that also means that a lot of the urban enhancement, in sort of urban scale particle number is from traffic and other primary sources. And so lastly, I want to tie this to exposure assessment and hopefully to epidemiology. And so I want to start with this by reminding everyone, this is the current network. We don't sort of have infrastructure in place the way we do for other major pollutants. And so what that means, there is a lot of literature about ultrafine particle health effects. A lot of that is sort of on single city sort of investigations, right? So sampling in a city, build a land use regression or other spatial model for that city, and that's typically built from mobile or distributed sampling. There are a lot of examples of that in the literature. Here's just one from our group. So this is a land use regression for particle number concentrations in Pittsburgh. It shows some of the stuff I've been talking about. That red sort of bullseye in the center is the downtown area with the highest traffic density. And you can also see sort of the major roads radiating out from the central business district. Collecting that sort of data can be really expensive and time consuming, right? We can't do this with filter samples. We can't do it with sort of passive samplers. You do really need to have sort of real-time instruments. Those are expensive. They're hard to maintain if you try and put a bunch out in the field. And so what a lot of studies have done have tried to use sort of short-term or quasi-stationary sampling to fill in these data gaps, right? So that you don't have to buy, a bunch of, a $50,000 widget or a $20,000 widget. You buy a smaller number and sort of drive them around. And so this is from a paper we put out last year looking at, well, how good are exposure models, in this case, typically land use regression type models, based on those short-term types of sampling. And the colors here are just different sort of methods of this short-term or quasi-stationary sampling. There's variability in the performance, but the average in each of those cases is about an R-squared of 0.4 in the model building. So it's describing about 40% of the variability. One thing that we showed is with sort of modest additional investments in sampling, model performance can improve. So the blue points there show LUR models that we built based on sort of 3 to 6 weeks of continuous sampling, and we get R-squareds up to about 0.8. And basically up to 3 weeks of sampling really improves model performance, and so we're describing a lot more of the variability. But we're a long way off from getting sort of national or big sort of spatial scale estimates for exposures, right? So keep in mind sort of what exists now in the literature is a lot of the time at a single city level. Some of you might have tuned into the webinar last week and heard Randall Martin talk about sort of national scale or continental scale estimates for PM 2.5. But there's a lot of infrastructure that goes into that, right? There's a national scale monitoring network. There's satellite data that helps sort of fill in the gaps between the monitors. There's simulations that help interpret the satellite data. And we really don't have that infrastructure right now, right? And even if we did, it's not necessarily clear that the satellites would help. They seem to be sort of more mass selective devices than number, right? But we're sort of a long way away from these big sort of continental scale estimates. And so then these are just a few sort of closing thoughts on what we would need to improve sort of exposure estimates for improved epidemiology. One is just more data is needed in more locations. And that might sound a little bit disingenuous because that's part of what pays the bills in my group, but really we do need more data, and it really needs to be sort of systematically and continuously collected. That's one of the real advantages of the EPA PM2.5 network, is that everyone's measuring the same thing. We probably need a bigger investment in measurement locations than we have for criteria pollutants, just because ultrafines are so variable. You know, for PM2.5, you can get away with a few sites per city. You know, for ultrafines, you're probably talking more like tens of sites per city in a mix of different land use types. As I said on the last slide, we're far away from sort of national scale exposure estimates. And, you know, to get there would require a pretty big investment in either monitoring and or sort of improvement of chemical transport models to fill in a lot of these gaps. But it's worth thinking about how to make those steps, right? Likely epidemiology and exposure data is needed if we want to push the policy needle, and to get there we need sort of better data. And so I just want to end by acknowledging that this work was funded by the US EPA through our Center for Air, Climate, and Energy Solutions. I want to thank Provat Shaha, whose name showed up a few times in this talk, and Alan Robinson for helpful conversations as I put this together, and thank the folks that provided me access to the data that I showed. So thanks everyone for your attention.
Thank you very much, Albert. That very interesting presentation on the challenges of making any sort of definitive statement about what exposures to ultrafines are. So thank you. The last presenter is Barbara Buckley. She joined the US EPA in 2007 and is a toxicologist in the Center for Public Health and Environmental Assessment, focusing on the criteria air pollutants regulated under the Clean Air Act. She received her PhD in environmental health science from Johns Hopkins, where she was trained in inhalation toxicology. Prior to joining the EPA, she's conducted biomedical research at Duke University on oxidative injury and antioxidant defense of lung epithelium and vascular endothelium. She is very widely published. So Barbara, please.
Thank you for that introduction, and thank you for the invitation, and to the previous speakers for their interesting talks. I'm going to talk about ultrafine particles and nervous system effects. What can toxicology tell us? And provide some insights from the 2019 Integrated Science Assessment for Particulate Matter. For those of you not familiar with the Integrated Science Assessments, or ISAs, they are documents produced by the EPA on the 6 criteria pollutants, air pollutants regulated under the Clean Air Act. And the 2019 PMISA was published last December and contains sections focusing on several different size fractions of PM, including ultrafine particles. A couple goals of this talk are, first I'll discuss the purpose and scope of the ISA. I'll talk about the key findings and limitations of the evidence relating ultrafine particle exposure and nervous system effects. And I'll share some thoughts about advancing the field. So the purpose of the ISA is to assess causality and inform hazard identification. And there's a variety of steps, as you can see here, all leading to the development of causality determinations using an established framework. And to get to that point, we consider evidence spanning many scientific disciplines from source to effect, and that's illustrated here. We incorporate evidence from atmospheric chemistry, exposure science, dosimetry, controlled human exposure, animal toxicology studies, and epidemiology, all to inform causality determinations. And in this talk, I'll refer to the combination of the animal tox and controlled human exposure studies as the experimental evidence. The scope of the ISA was designed to answer this question. Is there an independent effect of PM on health at relevant ambient concentrations? And to this end, there are a couple of inclusion criteria for the EPI and experimental studies. First off, the PM exposures needed to be relevant to ambient concentrations, and to us that meant less than 1 to 2 orders of magnitude above ambient. Second, the studies needed to include a quantitative or composite measure of PM, and for UFP that would be PNC or mass. And thirdly, studies needed an approach to disentangle the effect of the particle from the mixture in the case of source-based exposures. For example, if we were working with diesel exhaust exposure, a particle trap would help parse out the particulate versus the whole mixture effect. And in this way, the 2019 ISA is different than the one we published in 2009, where we didn't seek to parse out the particulate effect in the whole mixture studies. So here we'll go over some of the key findings from the short-term exposure studies. There was a single epidemiology study that found associations with behavioral effects in older adults, and several animal toxicology studies that found brain inflammation and oxidative stress, evidence for activation of a neuroendocrine stress response, and behavioral effects. And we concluded that the causality determination was suggestive of, but not sufficient to infer causality. Had we had more and stronger evidence, we may have decided on a likely to be causal or causality determination. Now, I want to point out that biological plausibility is part of our weight of evidence approach. And here is the figure from the ISA depicting the biologically plausible pathways underlying nervous system effects due to short-term ultrafine exposure. And we're mapping the evidence of relating exposure to endpoints. And we have a progression of effects from exposure on the left to outcome on the right. And I just want to highlight neuroinflammation in blue, the alteration of the HPA stress axis in blue, and the behavioral effects in yellow as common things that we found. Now, for the long-term exposure studies, we had a single epidemiology study that found associations with neurodevelopmental effects in children. And we had several animal tox studies that could be divided into 2 groups. One group of studies was in adult animals, and the focus was on neurodegenerative disease and upstream indicators of that disease process. And the second group of animals were young animals. They were developing and they were perinatal exposures. And in both cases, we found brain inflammation and oxidative stress, changes in neurotransmitters or their function, morphologic changes, behavioral effects, and our causality determination was again suggestive. And here is that biological plausibility figure from the document. And I just want to highlight in the adult animals, we have neuroinflammation in blue, and then to the right, neurodegeneration and behavioral effects. And in the developing animals, again, neuroinflammation and then impaired neurodevelopment as reflected by a morphologic change, a structural change called ventriculomegaly that was sex specific. And of course, in yellow, we have some behavioral effects and impaired cognition. Well, this evidence was not without limitations. And for epidemiology, we had a small number of studies, some uncertainty with respect to the spatial and temporal variability in UFP concentrations, possible exposure measurement error. And for the experimental studies, there's questions regarding the relevance of the experimental UFP exposures to ambient. There's a great deal of uncertainty about the mechanisms by which the inhaled UFPs affect the brain. And there's questions regarding the relevance of the rodent models for human nervous system effects. And the next couple of slides will detail these limitations, mainly for the experimental evidence base. So first off, are experimental UFP exposures relevant to ambient? Well, as we've discussed many times, they're often just defined as less than 100 nanometers in diameter. And amongst the 4 research groups that conducted the recent studies, they used different methods and particle sizes to assess the exposure health relationship. And there were particle concentrators in some cases, re-aerosolized particles that were collected on filters, a motor vehicle exhaust pass through a detonator, resulting in particle sizes from less of 100 nanometers to 300. In addition, there were 2 older studies from a Los Angeles group that used particle concentrators and generated particles less than 200 nanometers in diameter. So an important question for us is, should the experimental studies of the larger particles, and by that I mean the 200 to 300 nanometer particles, be evaluated as part of the PM 2.5 evidence rather than as part of the UFP evidence? And in our document, we had to bin the studies based on size distribution. And so this is a very important question for us as we try to understand the effects of the different size fractions. And secondly, the comparability of the experimental and epi studies. In the case of experimental, it was from less than 100 to 300, whereas in epidemiology, it was 10 to 700 in one study and not specified in the other. As far as exposure metrics, the tox studies usually measured mass or PNC, and the epi studies measured PNC. Turning to mechanisms, there's an important question here. What are the mechanistic pathways by which inhaled UFPs impact the nervous system? And we can group the pathways into direct ones and indirect ones. So for the direct ones, we want to consider whether solid particles or their soluble components must reach the brain for neurotoxicity to occur. Now, we've talked already about translocation today, and that is dependent on particle size, with the UFPs less than 200 nanometers in diameter, easily crossing barriers. And what we haven't discussed yet today is the fact that ultrafine particles can deposit in the nose, as well as in the deep respiratory tract or the alveolar compartment. And in the nose, they could translocate, they could deposit onto olfactory epithelium, and there could be a nose to brain pathway whereby the UFPs could translocate from the olfactory epithelium to the brain via the olfactory nerves. And then we have a lung to brain pathway where particles can translocate from that alveolar compartment, that deep lung, to the circulation, crossing the alveolar capillary barrier. And we could have a gut to brain pathway whereby ultrafine particles could be cleared by mucociliary clearance from the respiratory tract to the gut, followed by translocation to the circulation. So these are all possibilities, and it is possible that the neurotoxic effects occur due to the presence of the particles in the brain or soluble components in the brain, but there's all other possibilities, and I'm going to term them indirect mechanisms. So, and that would be things like a respiratory tract inflammation leading to systemic inflammation and brain inflammation, or to paracrine effects due to inflammation in that nasal epithelium or olfactory epithelium, and also to a neuroendocrine stress response, which has a capacity or capability of affecting every organ system in the body. Now, the ISA points to several of these pathways that I've just discussed, and the evidence is consistent with many of them, but it's not settled. It's not settled science. We don't really know how the particles are exerting, or the UFPs are exerting their effects on the brain. And turning to the other area of uncertainty, we have the relevance of these rodent models. How relevant are they for understanding human nervous system effects? Well, we had studies in the adult animals that focused on neurodegenerative changes, and we had studies in the developing animals focusing on neurodevelopment. And in some of those studies of neurodevelopment, it was neonatal pups exposed by inhalation. And these pups are developmentally equivalent to a third trimester human fetus. And in other studies, there's gestational exposures, and that involves that the pregnant mothers are exposed, and therefore the fetus is exposed in utero. So it's a different sort of model for looking at the perinatal exposure, depending on who gets exposed. So these relevant rodent models provide consistent evidence of nervous system effects in response to ultrafine particles, but We need to know a little bit more about the similarities between the nervous systems of the species to warrant concordance. We need to understand whether postnatal exposure in the neonatal mouse pups sufficiently mimics gestational exposure in humans. And we need to consider this last point. Are there differences in respiratory tract anatomy between the rodents and humans in terms of the amount and proportion of olfactory epithelium? And this is important because the amount of ultrafine particles depositing on the olfactory epithelium controls the amount that's available for olfactory transport, and that could be dramatically different between the species. And I don't think this is a settled question yet. Oops. So in summary, what can the toxicological evidence tell us? Well, the experimental UFP exposures are relevant, but there's differences between epi and experimental studies in terms of size distribution and exposure metrics, and that makes interpretation of evidence across the disciplines more complicated. We don't know exactly how the inhaled particles affect the brain. There is uncertainty about whether the UFPs translocate to the brain to exert their effects, or whether they exert their effects indirectly. And lastly, the studies on neurodevelopment need to take into consideration these differences in exposure route and the relevance for the developing animal. And just to close up, I'd like to mention a few thoughts about what may help to advance the evaluation of health effects due to ultrafine particle exposure. First of all, consistency in the exposure metrics and UFP particle sizes, both within and between epi and tox studies, would be very helpful. And second, we may want to reconsider the definition of UFP to take into account the ability of these less than 200 nanometer particles to translocate across biological barriers. And of course, we need to better characterize population exposure to ultrafine particles. And I had a few extra slides on mechanism, but I suspect I'm out of time, so I'll stop there. Thank you very much.
Thank you very much, Barbara, for the insight that we can gain from the toxicology evidence and its mechanisms and the questions that it brings up that need to be answered. So this concludes our formal presentation. I would like to thank all of the presenters for both their excellent presentations and their timely presentations of them, of the material. So we're now ready to move into the question and answer. And Alan, as I understand it, you will be moderating that. Are you ready?
All set. Thanks, David. So just a reminder to everybody in the audience, we're taking questions through the question and answer chat box that's at the bottom of your screen. And so if you have a question, please input it there. There have been a bunch of questions that have already been inputted, and I'll start the question and answers with those. We have about 25 minutes, so I want to just thank the speakers again for the excellent presentations. And so let's push ahead with some of these questions. And so I guess the format will be just if the speaker will just chime in and we can try to sort of moderate the answers there. So I'll just go down in order. So one question is what's the best way to measure UFP in the community? What UFP measurements are available and who is doing it? So if someone would like to take that, I think there was a number of different perspectives from particle number concentration to the end. Barbara was talking about sort of particles under 200 nanometers. So if someone would like to talk a little bit about particle measurements and address that question, please.
Okay, this is Albert. I can talk about that for a minute. I mean, sort of the simplest way is to get particle number counts from a CPC, and that's sort of what California is doing, which I think is pretty straightforward. If you're, already have some sort of regulatory site that's air conditioned, that's pretty straightforward to sort of get those to run because you're already having people, go in and check on the other monitors. Of course, you can do the whole size distribution that adds a level of, data analysis that has to happen to sort of process the data. And I think if you have like a nice air conditioned space, the CPCs are pretty robust. We ran into some issues when we were doing this rotating network and, trying to find 30 places, they weren't all nicely air conditioned. And, And that's where it would be good if there was some sort of, you know, more rugged or maybe low cost sort of method to do this, but none really exists at this point that I'm aware of.
I can add a few words. There's, you know, there is an alternative to using, instead of using particle number with a CPC that sometimes has problems like, you know, what's the lower size cutoff and so forth, is to use a diffusion charger based thing. So these measure currents. They're not weighted by size to the 0 power like like number counting is. It's more like size to the 1.2 power or 1.3 power. So it's still very sensitive to the small particles, but these things can be made very small and very cheap and very robust. So just an idea.
Anybody else? Barbara, do you have something from the health perspective you might want to add? I mean, you were talking, I mean, how valuable do you think PNC is from a health perspective relative to other metrics?
I think it's valuable, but we have to recognize that in those animal toxicology studies that sort of the accumulation mode particles are the ones that are being used. And so they are, the PNC may not be as meaningful as the combination of PNC and mass together. And to date, I haven't seen any studies mimicking ambient using particles less than that, although you can certainly use engineered nanoparticles to look at health effects due to the 30 to 50 nanometer range, but they may not reflect ambient.
Great, thanks, Barbara. Lydia, I was wondering, just following up on this, you were recommending sort of particle number concentration and was that mainly motivated by sort of available instrumentation, or was that motivated from a health perspective for the WHO report that you described?
Well, I guess these are both aspects. Like for a long time, we've heard that surface area would be the best parameter, but since surface area is not really measured, we don't have data. So it then is the discussion in circles. But in addition, there's been quite a number of epidemiological studies clearly pointed out to health effects in response to particle number concentration. So means that particle number concentration is a useful parameter and metrics for measuring exposure and for epidemiological studies. Also, we have such a large body of particle number concentration data, size distribution. So this is something which we understand very well. And the better we understand this, the better we can interpret the results and put things into perspective.
Great, thanks. Okay, well, let's move on to the next question. Let me ask, here's one from Jason Sachs. While there is some epidemiologic evidence indicating associations between ultrafine particle exposure and various health effects, there's still a large degree of uncertainty with respect to UFP exposures, considering their spatial and temporal variability. In Lydia's presentation, there wasn't much discussed regarding these exposure issues. In drafting the report you discussed, how did these exposure uncertainties factor into the report's conclusions, and more specifically in the interpretation of studies where often only one monitor is used where this variability cannot be captured?
Perhaps I can start answering these questions. I was asked to report just on the exposure aspects of the white paper, and we have also the toxicology and epidemiology. One of the biggest issues is in terms of epidemiology is the heterogeneity between the studies. Whether the heterogeneity is because the spatial or temporal variation wasn't taken into account, or whether it is because the instruments used resulted in different cutoff points, I'm not sure, but my feeling is that it is because the latter. There have been studies, epidemiological studies, with measuring from with a cutoff point of 30 nanometers or 20 nanometers. As I showed in one of my first slides, if we do this, we basically exclude the majority of the particle number concentration. So then you expect that there would be a variation. Spatial variation is important, and as Albert showed, that there is the factor of 2 or 3 within the city. Now, there's a factor of 2 or 3 within the city between the locations, but whether it is exposure it depends, because not necessarily the individual stays in these locations. In the studies we've done, and we are just still analyzing the results, because of the people movement, the exposure could be more uniform than it appears to be. But still, I think that lower cutoff could be one of the most important factors.
Great, thank you. Anybody else want to add anything onto that particular question? Okay, great, thank you. So how about one more sort of source-oriented? This is from Chad Bailey. How can the ambient measurements of particle number be reconciled with source-based measurements of PN, for example, in dilution samplers? In particular, the European solid particle number standard removes volatile particles, which can be a large fraction of ambient particles by number. Is there equal modeling capability to predict ambient particle number changes from particular source stack tailpipe emissions changes? So this sort of targets a bit Maddie, I think.
Well, yeah, I can say a few words, and maybe some other people can add to that. I mean, the European regulation for the solid number was partly due to practicality, right? I mean, they wanted to enforce the use of DPFs, which are devices that filter solid particles. And then basically nucleation is often such a kind of almost random looking event that large numbers of nucleation particles could really obscure the usefulness of a particle number measurement based on total particle number. So the kind of practical solution was let's actually count what we can limit regulatory wise. That's really pertinent to what a DPF or a GPF does. So you know, that's how to apply it to sources is I think I mean versus ambient is I think one of the unanswered questions, right? Because in the ambient, you're going to have lots of different types of particles that can evaporate and maybe not evaporate or recondense onto particles. So, you know, there's a lot of chemistry that goes on, and I'm not sure how well defined a particle number is at any given time or location. But maybe some of the other people can help answer that too.
Yeah, so you're saying that there's not good understanding between sort of tailpipe and ambient right now because of those changes.
Yeah, there's a lot of chemistry and stuff that and physics that occurs between that. I mean, something that's measured as a particle in a laboratory can evaporate in atmosphere, undergo chemistry, re-enter the particle phase sometime later, et cetera.
Great, thank you. Other people want to chime in on this one?
If I can add to this, some years ago we were asked exactly that question, and that was in relation to a Gladstone city, which is about 600 kilometers north from Brisbane. A lot of different emissions community was complaining there about one particular facility, and there were some difficulties in apportioning what's causing this, and eventually we were called to help. We were able to quite clearly point out to a specific facility, and this was based on size distribution. So the size distribution of particles from this particular industrial emissions at a community site 4 kilometers away, the size distribution was very different to the size distribution of other local sources. This wasn't a long measurement, but even so, we were able to point out to this. So there is, we've published that study. Then there's, I think, quite a potential in doing this kind of signature studies and based on this source apportionment.
Great, thank you. Anybody else? Okay, so how about one that might be for Tim? So I'd be interested in some indication of how the fleet composition turns over affects reductions in particle number as older vehicles age out.
Yeah, it's a very important question and gets to the importance of in-use emissions control programs. So these advanced after-treatment technologies are only as good as their penetration into the fleet, which in a lot of places is just relying on natural fleet turnover. So there's ways to accelerate that. California, for example, has had accelerated retrofit and replacement programs at their ports and has an in-use program in place. And I think thinking about in-use emissions controls, things like scrappage programs will be very important for these other regions that I mentioned during my presentation that are now adopting these filter forcing standards for diesel trucks. So places like India and China, Latin America, where you have these legacy fleets that can be very high emitters of PN. You won't be getting the benefits from these new standards until you can figure out a way to get those vehicles off of the roads.
Can you talk a little bit about the timescales for that process, Tim?
Yeah, I mean, it'll depend on the vehicle type and the region, but I mean, we're just anecdotally talking with Colombia now, where they'll be implementing Euro 6 standards in a few years, and they have trucks on their roads that are more than 30 years old. So that's going to be the target there. Other places in the US, you might see faster turnover, but for heavy duty trucks, there's long service lifetimes. So in order to fully benefit from these new regulations, we'll either require timescales that incorporate that fleet turnover or some complementary program to try to accelerate the introduction and scrappage of those older vehicles.
Great. Anybody else want to chime in on this one? How about something about non-tailpipe? I think Maddie talked a little bit about this, but has there been changes over time with the non-tailpipe? Maddie talked a little bit about the smoke part, brake smoke or whatever. Any sense of changes in non-tailpipe?
Well, with the brakes, I mean, we actually looked at those emissions. I'm more familiar with that. So the brake emissions correlate with the type of pad material. And for a while, for example, auto industry was trying to go to more aggressive brakes, give you that better feeling of, being able to stop on a dime, so to speak. And those often used more abrasive materials, and so the PM went up. Interestingly, that also correlated with the discoloration of wheel covers. And so that was a customer complaint. So we sort of were able to kill two birds with one stone and reduce emissions and improve the appearance of the wheels by putting in basically supplier-based requirements, technical requirements on the nature of the pads to kind of reduce that material.
So it sounds like there've been real changes in sort of non-brake wear emissions, non-tailpipe emissions as well over time.
Yeah, I mean, this was one example where it was motivated by the customer desire, but yeah, I mean, it sort of reduced the nasty part of brake particulate emissions for the atmosphere as well.
Great, thank you. Anybody else want to chime in on that one?
Alan, I'll just say briefly, I think that the non-tailpipe aspect will be increasingly important going forward as we have more and more zero-emission vehicles in the fleet. You're, of course, eliminating the tailpipe emissions, but the non-tailpipe emissions may remain an issue and increase in importance over time.
Great, and there's also evidence that they may even be higher for heavier vehicles, so they could become even more important on an absolute sense.
Yeah,
so
but electrification will help avoid that a little bit. So one of the things you do is to try to recover energy by braking, essentially by charging your battery while you're braking. So there's ways to try to improve that with sort of advanced vehicle technologies as well.
Great. Okay, good point, Maddie. So how about a question for Barbara? Are there any biomarkers available for UFP?
Biomarker. Not specific ones, no. There are biomarkers and they're subject to the same sort of issues as the PM 2.5 studies and other air pollution studies.
Okay, great. So nothing specific for UFP. How about non-traffic emissions? So, does anyone see the need to regulate UFP in industry emissions, power, steel, cement, waste incineration, as well as things like domestic heating with wood and coal? And we've talked a lot about traffic in this webinar, but what about these other sources?
So I can comment. I mean, some of the highest particle number loadings we saw were near industrial sites. I mean, they're also big PM emitters, and they're regulated under that sort of regime. But then I think, some of the mobile sampling stuff that came out of Oakland, there were metals recyclers are sort of this rising sort of source of interest. So I couldn't necessarily say like, yes, this is the set of sources, but I think I think in general we're moving into a world where non-traffic sources are gaining in importance, and UFPs are just sort of one example of that, where as traffic emissions go down, sort of everything else becomes relatively more important.
Great. Anybody else want to say anything on this one?
Well, if I can add to this, well, in Brisbane, what we see is in relation to nucleation events, they are mainly contributed from non-traffic emissions or from precursors coming from these emissions. So there's north of the city, there is a complex of sources, which is port, airport, and refineries. And when we see nucleation, and we see it very frequently, every second, every third day during the day, and more frequently than in the past, it is usually related to the sources rather than to traffic. But here we are talking about nucleation, which is precursors.
Great. So I had a question, another one, lots of questions on the sheet, but one is regarding the low correlation between PNC and PM2.5. This is a question from Patrick Kenny. Could you clarify whether this is temporal correlation or spatial correlation? I assume correlations across annual averages in different cities have not been examined. So anyways, this idea of how correlated things are and what it means from an epi perspective, I think you talked about this some, Lydia, and I think Albert mentioned it as well.
Well, one of the studies of which results I presented was specifically on this topic, and the reason for the study was because we've never really seen correlation between PM2.5 and PNC, but we've often heard about this, that there's a correlation, particularly from medical circles. And that's why we decided to do these studies, and we got data from 10 cities around the world. And the result showed that there's no correlation. Of course, you can think about a specific experiment, and in that specific experiment, when you have one particular source, when let's say one type of traffic, then you will find some correlation. But if you have a mix of airborne other sources, ambient sources, you simply don't see correlation.
Great, thanks. Albert or anybody else want to chime in on the spatial versus temporal correlation, long-term, short-term?
Yeah, I think I agree. I'm not sure of anyone who's done sort of the long-term correlation. I mean, definitely if you sit in one spot and measure number and mass, they are not correlated temporally. What we've seen in the work we've done is there's some spatial correlation. I mean, it's not, an R² of 1, but, the same sources drive sort of the spatial patterns for number and mass, sort of, and this is sort of at the intra-urban level. And they do seem to be, the variations seem to be, the spatial variations at sort of the inter-urban level seem to be correlated.
Anything else on that one? What about indoor ultrafine measurements? People spend a lot of time indoors. How well do ambient outdoor ultrafines penetrate into the indoor environment? Anybody want to tackle that one? No one talked about that, but that's certainly from an exposure perspective very important.
Well, we've done quite a lot of studies on this aspect, and recently in Australia, this was a very hot topic due to the bushfires, and bushfires are particle number concentration. So yes, this is a very important topic, and basically indoor PNC is mainly coming from outside. Well, unless there are specific combustion sources inside, but if there are no combustion sources, so then outdoor is the main source of indoor PNC.
Anybody else on that one? So there's a question here about low-cost sensors. There's obviously been a lot of interest and excitement around low-cost sensors. and they're sensors for PM mass. What about the prospects for ultrafine particle sensors? Low cost.
For the past 10 years, I've heard, or 15 years, I've heard from many different companies and many different colleagues saying that they are about to manufacture a low-cost sensor of particle number. It hasn't happened yet, so it may eventually happen, but I don't quite believe the statement now.
Anybody else?
So I mentioned a variation of that before. It's not number, but it's, you know, the diffusion charges can be made very small and very cheap, and not necessarily cheap. Now, but they measure something that's, you know, the amount of charge that a particle accumulates. So it's not quite surface area. It's maybe a little bit closer to surface area than anything else. It's a little bit ambiguous of what it exactly measures, but it's can be pretty consistent and a lot cheaper, more robust than particle number devices.
Yeah, so it sounds like, Maddie, a little bit, if we change your indicator from particle number, maybe there are some opportunities for some lower cost sensors potentially.
Yes, and these are a lot better than the light scattering ones that are very popular these days, because those light scattering ones are very much more oriented towards micron-sized particles.
Yeah, so a lot of the low cost are light scattering PM sensors. How about any other, anybody else want to chime in on this one? How about another one for Barbara? So if particles less than 200 microns or 200 nanometers, I guess, can easily cross barriers, do particles of larger diameters not easily cross those barriers? And are there differences in function? Whoops, someone is editing my document here. Why don't you start with that, Barbara, while I try to find the question again.
Yeah, to my knowledge, that's about the cutoff point for translocation. I know the slide that Dr. Robinson, you showed at the beginning from Dr. Casey's work or presentation last week, I think that was the Miller paper, and they looked at gold nanoparticles of different sizes. And in that paper, they didn't find much translocation of the 200 nanometer, but I think the broader literature does show that that is an appropriate cutoff for this translocation process. And I do think specifically the olfactory nerve transport pathway is operable up to that size.
Okay, great. And then the other part of that question was, are there other differences in function between ultrafine and larger particles, such as their ability to phagocytose? Right.
The clearance pathways are different. The ultrafine particles are not typically phagocytosed. The macrophages do a much better job with the PM2.5 particles and not these smaller ones. And the ultrafine particles are free to diffuse. So some of the studies have shown their presence within organelles. So within a mitochondria, for example, they're free to diffuse about a cell.
Great. Anybody else want to chime in on that one?
And the important point, which I mentioned in relation to the quasi-ultrafine particles, means that we should not cut at 100 nanometers. We should go higher, and in particular not cut through the mode. And therefore, in relation to what Barbara said, that particles up to 200 or even more are important.
All right, thanks, Lydia. So let's do one final question and then we'll wrap up. It's almost noon. So this is going to be another one for Barbara. Do you mind clarifying the potential gut-brain pathway? Were you suggesting the potential for clearance from the lungs and then passing into the esophagus, stomach, and small intestine for, for absorption or something else?
Right, that's what I meant. So the ultrafine particles can be cleared out of the lung by the mucociliary clearance, and they go up to the esophagus, are swallowed, and they go down to the stomach and into the intestine where they can be absorbed or I'm sorry, translocate across the barriers there. Yes.
Great. Well, we're just out of time. I want to thank, unfortunately, we didn't get to all the questions. I think we're going to pass these to the speakers, and I don't know if the plan is to try to get them posted with with the videotape of the recording of the presentation, but we'll see. But I wanted to thank all the audience for all your excellent questions. I wanted to thank the speakers again for excellent presentations. I also wanted to give a quick shout out to Katie Walker, who's one of the HEI staff that's helped organize this session. She was the HEI lead on the UFP report, the 2013 perspectives piece. So I think it was a great session. I think there is a lot of interesting new results on Ultrafine. There's still a lot of outstanding questions in terms of what the impacts are and what the exposures are, but I think that we're making progress. So I'd like to turn it back over to you, Eliane, to wrap us up.
Thanks very much, Alan, for moderating a stimulating Q&A session. And in closing, we want to sincerely thank the speakers and the chairs for this thought-provoking webinar on ultrafine particles and health. And we've clearly made some progress in the study of ultrafines, as Alan was saying, even as their characteristics and levels continue to change and pose new challenges. And we really look forward to seeing concrete steps taken to address the issues raised here today and future research. And finally, we want to thank you for joining us today. We hope you'll join us next week on May 13th for HEI's webinar on brain health and air pollution. Thank you all very much.
Thank you all.
Thanks, everybody.